Today, Team 29 will be presenting on federated learning, which is an innovative approach to decentralized machine learning. The team will be covering specific security challenges that come with federated learning. So, to kick things off, what exactly is federated learning? It's a decentralized machine learning technique where data stays on local devices like phones, laptops, or medical equipment, and only model updates are sent to a central server. This means raw, sensitive data never leaves the user's device, helping preserve privacy. Instead of pooling everyone's private data into one central location, we share what's learned locally. The server then aggregates these updates to improve a global model. It's essentially like crowdsourced learning without ever collecting the crowd's data. So here's a diagram of how federated learning works. So in step one, the server sends the initial model to all participating parties for local training. Then each party trains the model on its own data and then sends the updated local model back to the server. The server then at step three aggregates or combines these local models using an aggregation algorithm, creating an improved global model. And then finally, the updated global model is then sent back to all parties. It's new and improved, and then the cycle just keeps repeating. So a quick scenario defining this is, so imagine your smartphone learns how you type, which I'm sure everyone's does. So you wouldn't want these private texts that you send everyone every day to be sent to Google or Apple. So with federated learning, your phone learns from you. It keeps your data private and it only shares its training results. When combined with thousands of other users' learnings, the result is a smarter, more personalized AI on your phone, and it does not sacrifice anyone's privacy. So, of course, no system is perfect. Even though federated learning improves privacy, it also introduces new security challenges. Because model updates are shared, not raw data, attackers can try to manipulate these shared updates. This leads to what we call threat models, which include data poisoning, model manipulation, and privacy leakage. Our project will deep dive into these threats, the risks they impose, and how to defend against them.
Now that we know what federated learning is, let's go over the key advantages and limitations. One of the biggest advantages of federated learning is privacy. Since data stays on local devices instead of being sent to a central server, it minimizes the risk of breaches. Federated learning also allows models to be tailored to individual users. Since learning happens directly on the device, the AI adapts to personal behavior without needing access to centralized data. Finally, traditional AI requires constant data uploads. This consumes a lot of bandwidth. With federated learning, only small model updates are sent, making it much more network efficient. Now let's go on to some limitations. Since devices train models independently, hackers can try to manipulate the learning process. Attacks like data poisoning and backdoor injections can introduce biased or malicious updates. Unlike traditional AI, which runs on powerful cloud servers, training models such as federated learning locally consume CPU power and battery life. This can be a problem for low-power devices. A final challenge is that every device has different amounts of data, different processing capabilities, varying internet speeds. This inconsistency makes it much harder to train a high-quality global model.
So now I'm going to talk a little bit about security attacks. So even though federated learning keeps your data on your device, which is good for privacy, it doesn't mean it's totally safe. The problem is attackers don't need to steal your data. They can mess with how your model is trained. That can make the model less accurate, even sneak in weird or dangerous behavior. The two big attacks that I'll talk about in the next two slides are Byzantine attacks, which try to mess up with the training of the model, and poisoning attacks, where the goal is to teach the model something wrong on purpose so it gets messed up. So the first type of attack I'm going to talk about is the Byzantine attack. So Byzantine attacks aim to damage the training process of the model. This is dangerous because just one or two attackers can throw off the language of the process. So a little scenario is, imagine you got a bunch of phones training a keyboard app together. If just one of those phones is hacked and sends garbage updates like random nonsense words, then the server has no idea. It just averages everything, including all the bad stuff up. And even though only one phone out of all of them is acting up, it can mess things up for all the phones. That's what makes this kind of attack so sneaky and dangerous, is the bad updates can still look normal on the surface. The second attack I'm going to talk about is poisoning attacks. So poisoning attacks are different than Byzantine attacks. They're a bit more targeted. The attacker is trying to teach the model something wrong on purpose. A good example of this is with self-driving cars. Let's say someone puts a little sticker on a stop sign, and the car thinks it's a speed limit sign of whatever 60 miles an hour. If that image of the fake stop sign is used in training, the model will learn that mistake, and now all cars using the model might make the same error. So it's like planting a hidden bug that only shows up in certain situations. It's pretty dangerous if you think about it.
Alright, so in this section we are going to highlight the most critical defense strategies from 4 major categories used to protect federated learning systems from attacks. So first, under cluster-based defenses, we have federated learning white blood cell. So what this does is it groups local updates into clusters to spot poisoned updates, effectively disrupting any malicious conversions toward harmful models. Next, in the model metric-based category, we have federated anomaly analysis distributed learning, which uses cryptographic techniques to verify model integrity. It's designed to flag and eliminate suspicious models before they even reach the aggregation phase. For update statistics-based methods, the classic Groom algorithm selects the update that statistically is closest to the majority, making it highly effective against Byzantine attacks, where malicious nodes send conflicting or extreme values. And then finally, for performance-based defenses, DeepSight is an advanced solution that analyzes the model's internal structure. It prunes out backdoor triggers without degrading the model's overall performance, making it ideal against stealthy or hidden threats. Each method addresses a unique vulnerability, and in practice, combining these strategies significantly improves the resilience of federated learning systems.
Okay, in this session, I'm going to discuss about several techniques for privacy attack in federated learning system. And different from security attack which disrupt machine learning models' performance, privacy attack reveal information about data and client participant why this data information never leave the client. They train model or prompt to remember data information, and the attacker can obtain it by carefully analyze model outcome. However, this mostly requires either client-side or server-side knowledge. And there are two types of attack, including feature attack, which aim to recover data based on analyzing feature, and property attack, which aim to collect information about data attribute or distribution. So for feature inference attack, the target here is to recover client dataset information in the federated learning system, and based on the collected information, there are different kinds of attack, including gradient-based attack, where the attacker can observe gradient update from client machine learning model and reduce the private input data. Parameter-based attack, where the attacker uses adversarial and generative model to recover training data information by analyzing parameter and feature representation. And label inference attack, where the attacker can hijack and input a different input sample and observing the output to learn important feature using by the model. However, these attacks often require heavy either client-side or server-side knowledge to ensure the effective in collecting these training information. On the other hand, for property inference attack, the target here is to aiming to extract data attribute or distribution from client side. And there are two kinds of attack, where in population distribution, the attacker aims to infer the distribution of data by federated user side group, but it often requires both client-side and partial server-side knowledge. On the other hand, for individual distribution attack, the attacker can attempt to reveal if the target client or data attribute may or may not be relevant to the main federated learning system, but it often requires only client-side knowledge. However, the attack can enhance into incorporate with poisoning attack for a more effective attacking method, but it often requires server-side knowledge.
Hi everyone, my name is Shafiq Sufian Sapri, and now I'm going to present to you about the privacy defenses. So there's three defenses that we could apply, which is the client base, communication channel base, and server base. So first one, the client base. There's three steps, which is the differential, and we can start with the differential privacy defense. So for the differential privacy defense, it will preserve individual privacy while ensuring the data utility. It works by adding the random noise to the data. So next one, which is the perturbation defense, it is actually an alternative method against the non-DP based privacy attack, and it works by applying noise to the most vulnerable components, where, for example, the shared parameters and local data sets. It will reduce the amount of information the attacker can extract. And the last one for the client base is the fragmented federated learning. It ensures normal convergence of global model and protect it from security attack. And it also allows participants to privately exchange and mix encrypted fragments and their updates. So for the communication channel base, we start with the SMPC based defense. It's ensuring that the user will not have access to information about the others, and it's actually the variety of cryptographic primitives that are provided in the encryption methods for secure computation. And for the last one, for the communication channel base, is the defense of anonymous channel. It will provide unlinkability regarding the sender's message. This will break the link between the customer and his updates. And for the last category of the privacy defense, which is the server base, we start with the secure boost. This is actually when the data set is segmented based on feature dimensions in different aspects. This assembles tree model. And for the second one, for the server base, this is the federated reinforcement learning framework. It combines the federated learning with reinforcement learning while adding Gaussian interpolation to the shared information when each participant updating the local model. And last but not least is the FEDXGB, which is it leveraging secret key sharing technique. It provides protocols for global models, which is, for example, this security enhancement and prediction. So, as to conclude this project, there are some challenges that we can address. First, we conduct a literature review to provide foundational insights into federated learning, which is the FL systems, and examine the potential security and privacy vulnerabilities from a research perspective. This project aims to help readers to understand the attack surface and existing defense mechanisms in federated learning system. We also acknowledge that additional security strategies and protection framework exist within the federated learning research community, while offering more robust safeguards against attacks. That's all from me. Thank you.